Assalamu alaikum everyone. This is lecture 16 on control system engineering 1. We'll be starting chapter 6. The title of the chapter is stability. So this is one of the prime concern of any control system engineering is whether the system is stable or not. So whatever the rest of the analysis that we are going to do, say the transient or steady state error. So those are actually pointless if the system is unstable. So that is why it is inherently the first thing that we are supposed to do is figuring out whether the system is stable or not. Okay, so there's few definition of stability. So the first thing that we have is say from the perspective of the transient response, actually it has been defined. So as we know, the behavior, the system this response of the system CT is basically the summation of the two responses, forced as well as the natural one. Okay, so the natural response based on the natural response or based on the time for any time invariant system based on the natural response, the definition of the stability is given. There is three things. The first one is say stable system. Okay, then we have unstable system straight away to distinct position, unstable system, and then finally we have marginally stable, marginally stable system. So definition according to the natural response, the behavior of the natural response is if your natural response approaches, that means C natural approaches zero as t approaches infinity. So then we call this system to be a stable system. And the opposite one, so basically C and T, if it approaches infinity as T approaches infinity, then we call it unstable system. So what does it mean? So basically here it is vanishing. The natural response is vanishing as T approaches infinity. Here it is actually growing. The natural response is growing without bound approaching infinity. So this is the two distinct case. Then the third one is in between. Okay, so if your natural response is constant, neither growing, vanishing, or neither growing, so it is having a oscillation, then constant oscillation. Okay, so then call it a we call it a marginally stable system. Okay, so this remains constant in either in terms of magnitude or in terms of the oscillation. So this is a scenario. Actually, this can also be predicted from your pole locations because of the fact that, so if you're in this side, wherever the location of the pole, so it is always diminishing or vanishing, the oscillation. But if you are in the other side, okay, here, so in this zone, if you are in the right of plane, then it is always increasing. So these are the two distinct cases, and the boundary is your j omega axis. So if you're in the j omega axis, so either it will give you constant value or it will give you constant oscillation. So if you're at the center, then it will give you, at the origin, it will give you a constant value, or otherwise you'll have a pure oscillation that will never vanish or never increase in magnitude. So basically, these are the three conditions based on which we can actually define the stability based on your natural response. Okay, but what happens if you are no you're taking better a holistic way? So in that case, how can we define? So let's write if you also want to consider about the force response, uh, then what happens? So like a DC motor, in general, it is the natural response is to get settled and you are going to get a stable oscillation. But somehow you're applying a voltage or current, the force parameter part of it, which cannot be tolerated by the motor. So in that case, because of the force response of force input, the system can go into unstable zone as well. So that is why another definition should be there. So a system is stable if every bounded input yields a bounded output. So let me write it. Stable when if every bounded input yields a bounded output. Okay, so the term important here is every. Uh, okay, so bounded also, what does it mean? So if you apply infinity, you get infinity, then it's difficult to actually know whether the system is stable or not. Okay, so that is why it is the condition, every bounded, the input has to be also bounded. If it produces a bounded output, then actually you can say that the system is stable. Now, what it should be the definition of then the unstable system? So it will be unstable if unstable. Okay, so unstable if any bounded input yields a unbounded output. Okay, so here also, just like I'll try to relate with the pole as well. So now look at here, any bounded input, if it gives a output that is unbounded, in that case, the system is unstable. It is somehow also related to your pole. So because it doesn't make any difference how many pole in the other side, it doesn't make any difference at all. Rather, if any pole is in the other side, in the right half plane, your system is going to experience an exponential growth towards infinity. So that is why any bounded input, if it is producing any unbounded output, then actually your system is unstable. So if these definitions actually can give us, clarify the definition of the marginally stable thing as well. Okay, so the system marginally stable thing is means that for some input, there may be your system will be going into unstable zone. So the combination of both the thing actually can help us to understand what is happening. So based on your transient response or basically the natural response, as well as for the forced response as well. So combination of two can give you a better picture what is actually happening. Okay, so now exponential increase, exponential decrease, and all that as well. So one other factor that actually we should discuss is, though we are saying that on the j omega axis, if you have any pole, definitely they'll have in the complex conjugate except at the origin. So in that case, we are saying that it will exhibit a oscillation, sustained oscillation, okay, something like this. Now, but the point is, if you have multiple pole in the same location, the j omega axis, so will it still give you that marginally stable system? So basically, the answer is no. Why not? Because in that case, you will, in general, you have a equation something like this. Sorry, the cosine. Okay, so in general, if you have a pole in the j omega axis, multiple complex conjugate pole, then we have cos omega dt, something like this. Okay, so omega dt plus maybe phi plus minus phi, whatever it is. So this is the thing. But once you have multiple of them, say you have n number of them, n is more than one, then in that case, you'll have t to the power n will also be also multiplied with the response. So as t approaches infinity, t to the power n also should be approaching infinity. So therefore, does it mean if you have multiple pole at the same location on the j omega axis, the multiplicity is more than one, then as well your system will be going to unstable zone. So what you can say in the j omega axis, the best case scenario is having a oscillatory system, pure oscillation, or worst case scenario also it can actually go increase out of bound. So these are the things that is possible. Okay, so now some example is given in your figure 6.1. So they have discussed about some unity feedback system. So I'm not going in detail, but the point is what they have shown in the j omega axis, they have a pole somewhere here. Then if they're applying a step response, a step signal. So step signal, if there is no steady state error, it should give you 1. So if you have a pole somewhere here, which has a real and imaginary portion, then you are going to experience something like this, exponentially decaying to go to 1. So this is your stable system. Okay, and if it is on the other side, if you have somewhere here the poles, then what you're going to see is you're going to experience a behavior like, again, say you have zero steady state error, but because the pole in the other side of or in the right of plane, so now gradually it will actually increase the oscillation and eventually it will go beyond the control. So your system is going to become unstable. Now, one of the thing is that you're going to see most often we'll be actually have to deal with your, most often you actually have to deal with unity or non-unity feedback system. So if this is the case, then actually what are the, then actually how we are going to deal with the scenario. So in case of the feedback system, what is the problem is basically, even though we can actually predict what is our open loop pole location or the plant pole location. So this is our plant. Okay, so pole n zero is already known, say s plus 2, sorry, 10 into s plus 2, then divided by say s into s plus 4, s plus 6, s plus 8, and s plus 10. Okay, so now we know the pole location at 0 at the origin, at 4, minus 6, minus 8, minus 10. But whenever you have a feedback thing, so you have to do the multiplication and you want to find out a single block, because we said we need single block for the analysis, the technique that we have learned in your chapter 4. So so now to apply those, you need a single transfer function. So what is that one? So basically say this is T of S equal to GS the forward path transfer function plus 1 plus forward path transfer function, and the feedback is 1 here. So you have to find out, multiply, and then if you simplify a bit, you are going to get something like this: 10 into s plus 2. So that 10 into s plus 2 will be also appear in the denominator. So after multiplication, we are adjusting. So what we are going to get is s to the power 5 plus 28 s to the power 4 plus 284 s plus 3 plus, I should have done it a bit large. Okay, so 1232 s square plus s square plus 1930 s plus 20. Okay, so the denominator is a very large number. So it is having an order of 5. So now, without factoring this equation, the denominator equation, it is actually difficult to tell where the pole location. If we don't know the pole location, actually we are not certain about their whether the system is stable or not. Like in the plan itself here is stable, but after the feedback, what is the scenario? What condition change? We have no clue about it because of the fact that we cannot easily factorize this one without the help of either the computer or without the help of the maybe some calculators. So nowadays it is available, but at the very beginning, once this control system was actually been developed, there was no such technique to easily factorize this parameter. So that is why it was a bit difficult at that time. And that is why one of the technique was developed. The technique is known as Routh-Hurwitz criterion, according to the inventor, Routh-Hurwitz. Okay, so Hurwitz criterion. Okay, so what he has done is he has formed a table. So the table is known as a Routh table. And then based on that table, he calculated it is possible to interpret the table as the location of the poles. Okay, so location of the poles. Sorry, not exact location, in which segment they are. Okay, so poles. So actually, what can be done is we can predict three things, not location. Be careful, exact location is not possible. So what you can say is how many pole in the left half plane, how many pole on the j omega axis or origin, or how many pole in the right half plane. This sort of information actually can be figured out from the interpretation of the table. Okay, so this is how we can do. So, but exact location, not possible. Only the information is there. How many pole in which location, that can be calculated based on this criterion. So now you may ask that nowadays you have the computer and the programs, or even some scientific calculators can do it, then should you learn it? Actually, it helps you to design, okay, in designing rather than analyzing. So analyzing and figuring out where the poles are in which zone. More than that is, it actually helps you to figure out solving your designing problem as well. And also it can give you, if you have some unknown parameter in the denominator of the equation, it actually of the closed loop expression, then it also helps us to find out the range, for which range of values it is actually uh, remaining in the left half plane or moving in the other way around. So all this thing, actually the designing is more important. So that is why, as I already said, that fundamental things we actually have to know, because whatever the advanced thing we are going to apply or we are going to use, that has to be designed somehow by the engineers. Okay, so in that case, like if you have to write the program, it's a, you are the first person to write the program, how to figure out the routes table automatically. So in that case, you have to know the procedure first, then actually you move forward. So that is what, yes, even though practically maybe you don't have to deal with it, because in a single command in the MATLAB, you can find out the exact pole location. Based on that, you can easily predict that not only whether it is stable or not, and how stable or how oscillated it is going to be. So all this information can also be figured out from your pole location. So that is why nowadays you will find that it is not that helpful at times, but still we have to have the fundamental knowledge so that actually we can use that to a good effect. So now say so two parties there. One part is creating the table, and then interpreting the meaning of the table to find out the zones in which the poles are. So let's start with the first thing, creating the basic route table. So creating a basic route table. Let's say we have a simplified scenario. We have a closed loop transfer function given already, and in terms of coefficients, maybe we're not interested about the numerator, rather the denominator, say a to the a4 s to the power 4 plus a3 s to the power 3 plus a square s square plus a1 s plus a0. Okay, so this is the case. You have rs, cs by default. Now, how to form the basic table? The pattern is whatever the highest order of the s of the denominator. So starting from that one, you have to write the rows. Okay, so s to the power 4, s to the power 3, s square, s to the power 1, s to the power 0. Okay, so this is how you have to set the rows, and then you have to fill up the table. So based on the coefficients, so say the highest one, A4. So A4, if you want, you can also draw some lines so that will help you. Okay, then what you have to do is coefficient of highest order, that is s to the power 4. We have to write that. So A4, then A3. Then after filling up only first two, highest two, then you have to follow a zigzag pattern like this. So next will be going there. So say your A, okay, so next one will be A2. Then again zigzag. So you will be next one, that is A1. Then finally again with another zigzag. Okay, so this is a way of filling up the first two, the first two row of this table. Okay, so bottom line is we are following the pattern, something like this. Okay, so filling up until it goes to the last parameter. Okay, so this is the pattern we are going to follow to fill up the first two rows of the table, row table. And then you have to figure out what is the third one, third row, then next row, next row. So this is how you have to do. So what is the procedure for filling up the third one is, let me erase it a bit so it will help us. Okay, so now what is the next procedure? What we are going to follow is finding generating 8. So basically these two will be multiplied together, then this two will be subtracted from that, and then you have to divide by this parameter again. So something like 8 is being created. Okay, so this is the thing you have to do to figure out this parameter. Say this is your uh, uh, next parameter. We can call it B1 maybe. Okay, so B1, B2, B3. Okay, so then maybe C1, C2, C3. Okay, so goes D1, D2, D3. So this is how you have to fill up the table. So this formation of the 8 is actually going to give us the B1. So what is the formula for the B1 then? The B1 is A3 into A2 minus, so this one, A3 into A2 minus A4 into A1 divided by, again coming back to A3. So now this is how you have to find out the B1. What about the B2? B2 is forming the 8 again, but you have to be careful is that every time we're forming the 8, the first column will always be there. Okay, so basically we are forming a table based on the first two and the next two, something like this. So, and also if there is nothing given, say if we want to form using this first column and the next one, as you can see, one parameter is missing here. So that parameter will be always replaced by a 0. Okay, so what about the next 8? So next 8, that is your B2, will be actually filled up by forming 8 again. So starting from here, this one will be multiplied with this. Then this will subtracted from the multiplication of these two, and then again divided by A1. So basically, as you have noticed, it is always being divided by this parameter here. So what we are going to get here is A3, A0 minus A4 into 0 divided by A3. Okay, so similarly, you can actually figure out the rest of the parameters, like we have to calculate what will be C3. Okay, so for C3, we have to again form. Now we are concerned about these two rows. Based on these two rows, we have to find out what will be the values of these rows. So again, you have to form a 8. So basically, you will have something like this. So basically, what we are going to have is B1 A1 minus divided by this, that is A3 B2, and then finally again divided by B1. Okay, so what about, sorry, actually by mistake I have written C3 here, it will be C1. Okay, C1. Similarly, C2 can also be figured out. So for figuring out the C2, what we have to do is we have to multiply this one with this one. Then this one will be subtracted, then again divided by this one. So basic idea is forming the 8. Okay, so similar idea will be for C3. So basically there is nothing here. So it will be multiplied with this. So eventually it will be becoming 0. So this is how you have to form, but in the book they have some determinant they have used to figure out. So it's up to you. This is how it is simpler to me. So I try to follow this. If you feel it difficult, then actually you can follow the book's procedure as well. So let us try to figure out one example. So let's example 6.1. So in the example 6.1, one unity feedback system is given. Somehow you'll find that you may have non-unity feedback system as well. So you just multiply and figure out the solution of the closed loop transfer function, and then just figure out the denominator of it, which is your characteristic equation. So this is the scenario, plus minus, careful about the signs. And then you have 1000 divided by s plus 2, s plus 3, s plus 5. And now you have your CS. So you have to find out the T of S. T of S is G of S divided by 1 plus G of S, because H of S is 1. So basically 1000 divided by S plus 2, S plus 3, S plus 5. Then you have 1 plus this parameter. So basically S plus 2, S plus 3, S plus 5 plus 1000 divided by your this parameter S plus 2, S plus 3, S plus 5. Okay, so eventually this one and this one getting cancelled out, and what we are going to get is, as you can see, what will be left, the last parameter based on this 6 into 5, 30 will be added with that one. So S cube also will be there. And now if you just do a bit of simplification, then what you're going to get is 1000 divided by, just multiply. So S cube plus 10 S square plus 31 S plus 1030, 1030. So now first thing is the highest order of S is S cube. So you form the Routh table based on that. S cube, S square, S to the power 1, S to the power 0. Then next thing is to form the table. So populate the first two rows. So basically the coefficient of SQ is 1, the coefficient of S square is 10, and the coefficient of S is 31 in the zigzag pattern, 1030. So this is the scenario. Now, what will be this parameter here? Okay, so you have to form the 8. So if you form the 8, what we are going to get is, okay, so we have to multiply these two, 10 into 31 minus 1 into 1030. So 1 into 1030 divided by 10. Okay, so it will be 310 minus 1030. Okay, divided by 10. So eventually what you are going to get, if we just use a calculator, is minus 72. Okay, so put the value minus 72 here. And what about this parameter here? For this parameter, again, we have to do the thing, but as we know that if there is no parameter, it is 0. So now if you form a bigger 8, starting from here, multiplying these two, subtract. So basically, both the parameter will be 0. So we can say we have a 0 here. Okay, now what will be the parameter here? So for this one, actually, we have to form the 8. That is, we can multiply these two. Then we subtract again this and then divide by this one. So basically what we are going to get is something like this. 10, sorry, 72 into 1030, then divided into 0, because 10 into 0 is 0, then divided by minus 72. Okay, so we have something like this. Minus 72 minus is going to cancel. So basically this parameter is going to sit it here, 1030. Okay, so now the table is formed. So now next thing is how to interpret the table. So the criterion that tells that how many sign changes you have in your first column of the table, how many sign changes you have, that many number of poles should be in the right half plane. So if we now look at this one, how many sign changes we have? The first one is plus, second parameter is also plus, the third one is minus, the fourth one is plus. So we can say there is two sign changes, one from plus to minus, then from minus to plus. So our conclusion is, for this particular system, two poles are on the right half plane. Okay, so this is our conclusion. So is your system stable? Definitely not. Your system is not a stable system. So this is how you have to form the table, and then you have to interpret whether you have a sign change in the first column or not. If you have a sign change in the first column, it means that your system is having that many number of poles on the right half plane, and accordingly your system is unstable. Now, few things what we have to be careful is, first of all, say in this particular example, let me erase some portion, then let me discuss it. Say okay, so again, I think it will be better to redraw than erasing. Say then 8s cube, s square, s1, s to the power 0. So say somehow, I'm not saying that we have some parameter here like 10 and 1030. Okay, in this column. Sorry, in this row. So now this, you can see there's a common factor of 10. So actually they can be divided, both of them can be divided by 10. So you can bring 1 here and you can bring 103. So the number can be reduced. So any row can be actually divided as well as multiplied with a common factor. Say somehow in the next row you have something like this, 1.5 and say 4. Okay, so now 1.5 is difficult for calculation. So rather, if you have a whole number, that is better. So you can actually multiply this row with 2. So you can bring 3 here and then you can bring 8 here. So it will not affect your result if you only multiply or divide by the common factor. Or sometimes you can also multiply with a negative number. Okay, so -1 or something like this. So eventually it will give you the same thing. Okay, so same result will be achieved after the multiplication or division of the common, the entire row by the same common factor. So this is one thing. And also another thing is a quick note, maybe say you have s cube, or maybe say s to the power 5 plus 6s to the power 4 minus 3s cubed plus arbitrary 7s square plus 8s plus say 9 or 10 whatever. So this is available and we're not interested about the numerator at all. So now by looking at this system straight away we can say that the system is unstable because you have a negative sign here. Why we're saying that? A quick just by looking at a glance we can say the system is unstable because of the fact that if all of the poles are in this side or maybe on the real axis, then the multiplication will be something like this: s plus s1, s plus s2, a2 maybe. Okay, so any multiplication of this pattern will never generate, because all of them are positive, so will not generate a negative sign in the characteristic equation. So if you have any negative number, then straight away a negative sign, then you can straight away say that the system is unstable because it has been produced by some s minus a, maybe a3 or something like that. So this negative sign is a direct indication that your system is unstable. Okay, so this can be identified easily. Only the fact is that if all of them are positive here, then you're not sure. So in that case, actually, you have to go for Routh-Hurwitz criterion. So that will give you the number of the pole in the right half plane, but not exact location where they are. Okay. Okay, so now another thing is, say in your particular system like this one, this parameter is not vanished. So basically S is not there. So if S is not there, so what should be the system response? And if say neither of them, say this one is also near. So you can always assume that 0 s to the power 4 because of the formation of the table. So 0 into S, this is what you can do for the formation of the Routh table. But this one has a specific meaning. What does it mean if say S term is not there, S to the power 1 is not available. So S to the power 1 is actually, as you can relate, is basically d by dt. Okay, so what does it mean? D by dt of this parameter, and also from the characteristic equation of the second order, we know that s square plus say twice zeta omega n s plus say omega n square. So basically, this one gives you the damping thing. So if the damping is not there, then also we can straight away say that the system is marginally stable, okay, or unstable, okay, based on the fact that maybe because of the fact that you have multiple pole in the same location on the j omega axis. So this is also a possibility. So, but as you can see, if this S parameter is missing, the best possible scenario is a marginally stable scenario, but worst case is unstable system. So based on all these ideas, actually, we can go for one example. Say skill assessment exercise 6.1, skill assessment exercise 6.1. So they have directly given you the characteristic polynomial p of s equal to 3 s to the power 7 plus 9 s to the power 6 plus 4 s to the power 4 plus 7 s cubed plus 8 s squared plus twice s plus 6. So the coefficients are known. Now the first thing is always the formation of the table. Highest order is s to the power 7. Then you have s to the power 6. Then as you can see, okay, sorry, actually I have missed that one. Plus 6x to the power 5. Okay. So s to the power 5, s to the power 4, s cubed, S square s to the power 1 s to the power 0. Now place them according to the zigzag pattern that we have said. So basically 3, 9, then you have 4. I think that next one, sorry, this is 6 because s to the power 5 is we are missing, which is supposed to be here actually. Okay, so this is your, it should be 6. Then you have 4. Then you have 7, 8, 2, 6. Okay, so there is a common term. So actually we cannot apply that common term here. So don't worry about that thing. If it is not available, we don't have to worry about it. Rather, we can just directly apply the formula, and that formula is forming the 8. So basically, if you form the 8, 9 into 6 multiplied 8, then divided by subtracted 3 into 12. So, and then you have to subtract 3 into 4. So it is, which will be equal to 42. Then you'll have to divide it by 9 again. Okay, so this is how you have to do it. And directly you can put the value, or you can find out the fraction. So you can also keep that one. So it's up to you. So basically what we are going to get here is so we are keeping it, finding 4.66. Okay, keep in that way. Okay, next thing is forming the bigger 8. So 9 into 7 and 3 into 8 divided by 9. Okay, so 9 into 7 minus 3 into 8, then divided by 9. This is the second parameter. So let's do that. 9 into 7 minus 24. Okay, so divided by 9 again. So approximately 4 point something, 4.33 we are going to get, or you can keep also as a this number. So 4.33. If I'm not making a mistake. Okay, so next is forming the next 8, that is 9 into 2, 9 into 2, then minus 3 into 6. So 9 into 2 is basically 18 minus 18. So we are going to get a 0 here. Okay, so this is what we are going to get eventually. So it will be more convenient actually if you write something here. Otherwise, we are maybe getting a bit confused. So we'll have 4.33 here and other 0 here. And the last parameter will be automatically 0 because of the fact that the parameter of a particular one is coming from the next one, isn't it? So next one is not there, so it will be 0, 0. So we are going to get a 0 here. Okay, so next is based on, there is 4 here. So you multiply here again, and then you have to multiply the next parameter here, and then you fill up this one. And similarly, gradually you are going to see that the last one is just having 1. So again, based on the condition, whatever the sign of this one, say here, still we don't have a sign change, but maybe somewhere here we'll have sign changes. So based on that sign changes, we have to decide how many on the right of plane. So in this case, actually there will be 4 sign changes in this particular one. So if 4 sign changes is there, that means you have 4 poles in right half plane, and the rest of, because you have the order of 7, so rest of the 3 is in left half plane. So what about the system stability? A single pole in the right half plane is enough to make your system unstable. So in this particular case, you actually have 4 of them. So definitely there is no question that your system is going to be unstable. Okay, so let us go to the next one. So we have 2 spatial cases. If somehow there is a 0 appearing in the first column, then what will happen? Okay, so this is one spatial case, and the other spatial case is there is the fact that what happens is if your entire row is becoming 0. So there is 2 special case possible. The first one is 0 only in the first column. So 0 only in the first column. This is one case. So the other one is 0, the entire row is 0. So let us first discuss the problem with associated with them in formation of the table. Then actually we'll go with a specific example to see how to deal with them. So what happens if any particular value in the first column is becoming 0? So say s cube, s square, s to the power 1, s to the power 0. So what is happening? Say this parameter somehow becomes 0. Okay, so say you have 2, 1. Okay, so arbitrary values may be there. Now, what is the problem with the first? If you have a 0 at the first column, is basically we are forming that 8, isn't it? So we are always multiplying these 2 value, then we are subtracting these 2, then again we are divided by this value. So if you have a 0 in the first column, you actually have to divide by 0, which will give you a infinity. Okay, so this is what is unexpected. So that is why if you have a 0 at the first column, then it is difficult to form the rest of the table. So there is 2 ways to solve this one. We'll discuss both of them. So one way is 0 has been replaced by a very small number, very close to 0, epsilon. So epsilon can be just 0 plus, or epsilon can be just 0 minus, very close to 0. So based on both the scenario, you actually have to decide, because we are just interested about the sign change. So if we can somehow figure out what is the sign, that should be good enough for us. So we'll be taking a very small number, very close to 0, and based on that we'll try to fill up the rest of the table in terms of epsilon, and then we'll see whether how many sign changes we have, and if there is any sign change, so your system is unstable because that many number of pole is in the right half plane. This is one way to deal with it, and the second way to deal with it is if you can change the order of your characteristic equation. Okay, so reversing actually. So what we are going to do is we'll replace, we'll define one thing, that is d is equal to 1 by s, or conversely s equal to 1 by d, vice versa. So we'll define that way, and then actually we'll change the order of your polynomial. So what we are going to do is basically, if you have something like this, s to the power n plus a n minus 1, s to the power n minus 1 goes up to a1 s plus a0 equal to 0. So We'll replace s by 1 by d. Okay, so 1 by d, and if you put it, then what we'll have is 1 by d to the power n plus n minus 1. Okay, so 1 by d to the power n minus 1 plus goes on up to a1 1 by d equal plus a0 equal to 0. Now if you multiply, you can factor out 1 by d, 1 by d to the power n. If you factor it out, then what you're going to get is 1 plus a to the power n minus 1, 1 minus d to the power minus 1, plus goes on up to a1, 1 minus d. Okay, so 1 minus n plus a0, 1 minus d to the power minus n equal to 0. So now, since all of them are in the negative domain, 1 by d, 1 by n to the power minus 1 is actually d, 1 by d to the power minus 1 is actually d. So if you just rearrange, and it is just multiplying factor which can be sent it to the other side. Okay, so what we are going to get is something like this. 1 by d to the power n. You can take it to the other side, multiply with 0, so it's vanishing. So what is left is 1 plus a n minus 1 into d plus goes on a 1 b n minus 1 plus a 0 d n equal to 0. Okay, so what it actually means, say you have a system like s cube plus 3s square plus 2s plus 5 equal to 0. So what you can do is, if you set s equal to 1 by d, what is if this one will have the highest order now, 5d square, sorry, d cube, just like here. As you can see, this one is having now the d to the power n. So now it will have 5d cube. Then the next parameter will be this one. So plus 2d square plus 3d plus the coefficient of s cube is 1. So 1 equal to 0. Okay, so once you have this equation, now again using this equation, you actually have to try to find out the Routh table, and then after forming the table, again you look for how many sign changes in the first column. So this is how you have to do. This is a second approach, second method. But the second method, if you are unlucky, then also it may happen that in the second method as well, some of the row is becoming 0. Some of the row in the first column is also becoming 0. So that is why it is not that convenient. Rather, I prefer the first method, which is assuming the epsilon, which can be 0 plus or 0 minus. Okay, so this is the first one. Don't worry, I have just in this one, I have just explained the method, but I haven't used the example to solve it. I think the time is almost close to 1 hour. So that is why the examples I'll try to give in the next class. So this is one problem, that is finding a 0 in the first column. And the second problem is finding a row with entire 0. So say again s to the power 4, s cube, s square, s to the power 1, s to the power 0. So now somehow one row is becoming 0. Okay, so there is a mistake in this assumption, but still say here somewhere we have a entered 0. So what will happen now if you are, whenever you're trying to form the 8, So both the parameter, because both of them are multiplied with 0, so you can proceed further. So whatever the rate you're trying to form, so it will always giving you some undefined values. First of all, the 0 divided by 0. So now that is why this is also a spatial case, and on this spatial case as well, actually we have to apply one method. We have to form a equation based on in whichever row you're obtaining it, the row before that one. We have to use a equation called auxiliary equation. So it's a P of S, and then we have to differentiate that P of S and then set it to whatever the values you're getting, the coefficient of that one will be coming to the 0. So 0 will be replaced by that coefficient, say A0, A1, A2, whatever you are getting after differentiation. Okay. So don't worry, I'm just giving you the whole idea how to deal with the two spatial cases, only the theoretical part of it. But don't worry, we'll be actually going with some example of this one. So I'm actually a bit sick today, so but still I have to cover the thing. So when I felt a bit little good, then I started recording the class. So maybe when the class is not up to the level of the previous classes. So if you have any question, queries, you always keep it in mind, and you can always ask in the review class. I'll actually appreciate that one. So and I do apologize if there is inconvenience because of my sickness in this recorded lecture. Okay, and see you in the next class, inshallah.